Welcome to CMS Manhattan series about CMS Manhattan project. Today we're going to go through our transformer model. It looks like similar like GPT model. We use transfer mechanism. This is transfer model type. And why we start develop that? Because some license, free license can impact on your business. For example, meta license says something like, if you exceed number of clients which use your model, then we have to make new agreement. Of course, it impact on your business. And for example, if you use Google license, if you can find the same height meaning in license, and even licenses looks very bad, like Apache license. Somebody from company, Google company, can go and say, okay, we think we don't use a license properly. And anyway, if they take you in court, your client will think, oh, something wrong, and risk management company automatically will change solution supplier. You will lose business this company. That reason we decided to develop our transformer, our LLM based on transformer, because the transformer is actually most common way in very big language model in modern business, such as Grok, ChatGPT, such as Meta. It's a similar thing. Yeah, if somebody would like to implement our transformer, own transformer, I can implement for somebody. It costs, of course, money, over $1 million. If somebody would like to do, just I would like to go brief how to implement my transformer for better understanding. I use a Java JDL library. It's made by Amazon. Let's go to architecture transformer which I made. That is our GPT LLM. Yeah, we have a class loader which build layers in my transformer. That is architecture of my GPT model. As you can see, we load layer one by one in sequential block. Each layer extended from abstract class. GPT, JDL framework. For embedding layer, I use. Let's go through two layer here. We have a embedding layer here. We have two layers, embedding layers, to improve our embeddings and understanding context better. Then we have a transfer block, which corresponds to transformer architecture, and this block is special, which convert your model to transformer model, transformer model. Yeah, and then go normalization layer. Just I used basic class from JDL transformer normalization, which will improve some issue regarding machine learning to move fixed embeddings to last layer, to layer which contain logits, logits which actually embedding ready to predict, and we apply function softmax to improve prediction, to make small values, make more smaller, and bigger values make more bigger to improve prediction. That is actually a short explanation of this model, and we can go dive. You can see how I handle with classes with JDL to implement my transformer. And we have a embedding layer, custom embedding layer, which use Xavier algorithm with Gaussian parameter. that earlier for transformer models, and then we have I use second embedding layer here, and I use the same algorithm here. But if you can take a look, difference is we define different shape for first layer and second layer. Yeah, I can show in code how we define here. This is a shape which I assign here. Shape made from vocabulary size, which I defined over here, and embedding size for model, yeah, dim, model dim, and yeah, let's go back. And second layer, a little bit tricky. It's a little bit smaller. You can see we have a max sequence length. This is a parameter for context which you use with your GPT model in RAD mode, in inference, if somebody would like to like this word, the inference mode. Yeah, this also just define shape here, and it should define the shape here. This strategy designed to improve better understanding of context. This one just make meaning for every sentence, and here next layer will make embedding, which will know about words before and after to better understand context. Yeah, next we go to transformer block, which we decided to make because this transformer LLM, and we have parameter for this, a number of hit and attention layer, and number of transformer block. This is regular for any GPT model like this here. Let's go dive and take a look how we implemented transformer block. We have we added many children, other blocks like attention layer. Attention layer contains some features like a number of heads here, and 1, 2, 3, 4, and so which actually will find some patterns in our in our embeddings to better understand context, and to filter some better embeddings which we got from embedding layer. And for example, model can decide provides few 3, 5 answer for your after semantic search to your attention layer, like you do in RAG system, that similar one. And this attention layer will apply some mechanism like cosinus similarity to find better one, to find better embedding, yeah, to predict. There is some mechanism which play in forward internal methods to play with logic over here. Next, we go in normalization layer. This is basic standard class, not designed by me, from JDL, which do some normalization and reduce number of issue which related to machine learning, like issue with gradient numbers, which can impact on machine learning quality. And after that, we go to feed-forward layer, and the feed-forward layer was designed with 2 linear classes. Every class have a parameter embeddings before activation function and after, and why 2 different embedding size? Because this embedding size have some strategy to get more information, and after that, just find better mm, find better result, process more data to get better result. This will improve better context, will 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 understand better context. Yeah. And this is a lot of function. This function is designed to activate some neurons in our feed-forward layer in order to forward direction to correct neuron and to find better response. Simple explain. Okay. By increasing this parameter, feed-forward DIM, we will extend more opportunity to process more data, to find better context, and find and direct our trend, our vector to particular to more appropriate neuron. To direct after that to last layer with logits. Go back to our architecture over here. Next, okay, we designed transformer layer. After this, we go with normalization layer. Normalization layer will fix some issue related to machine learning on previous layer and apply some function like Adam, to fix some issues. And then we have a last layer which contains logits. We have to define vocabulary size here to help system find better prediction. That again, this layer also use softmax function to find better neurons to our output. To our output. How softmax work is very simple. Take a smaller value, make more smaller, and take big value, make more bigger to improve prediction. Then how it work. That's it. And let's back to our parameters. This is the dictionary size which you have to get from your tokenizer. This one is embedding size for your model. This is number of head attention for our transformer block. This numbers of layer. Our transformer block, it's regular 6, and this is a number of words in our context when we talk to chatbot, chat history, for example. And this one is double, and for our feed-forward layer to also improve better context and understanding for classification tasks. For example, this also will improve context understanding for task classification, for example. That's it. This is basic architecture of my model, which I made. Welcome. If you'd like to design a model for your company, I can design. This is code belong to me. Don't copy this. And after this code, don't share this, copy this. Just if you need to extend that, just call me. I will design model for you. Even we can design multimodal model by improving our custom our embedding layer. For example, embedding layer, we can combine many embeddings from different models, from sound embeddings, for example, and picture embeddings with text embedding together. It's very simple. We'll create our new array, and we copy pictures embeddings and text embeddings and sound embeddings in new array, and we'll put everything in our custom embedded model and play with our, of course, parameters over here to make it better. Then we can add some additional features if we'd like to do. Just, for example, we can add some image position to, if you, for example, if this your robot brain, your robot can understand position where he stand in your room. Yeah, the same thing. We have to take some model which generate embeddings for position of your picture, and if you need other features for your robot, we can put everything together in your model. That's it. Call me if you need that.